Pay my respect to the Ukrainians who are still fighting, unfortunately. But then I want to talk about complexity. Remember the paradox? So have you found solutions to it? Did you try to find a solution? Remember, when you have a time complexity, means over all admissible executions you take the most. So it's not just one execution, huh? Maximum time for all admissible timed executions. And we have this nice little algorithm here that does a broadcast. Simple algorithm. And I was asking you to show me how this can slow down when the messages go fast. So anyone found a solution to this? No. Did you try thinking about it, at least? Oh, well, okay. Kind of disappointing, but I will explain on the board what's going on. But for that, tomorrow there is a lab session, one of the preparatory sessions for the midterm and for the final if you want to. So don't forget, tomorrow there will be a lab session at the usual slot in the afternoon. Okay. So here's a source node. Here's a network. Let me just make it a circle. Here's another node. And let's say we want to make it slow for messages when they go faster. So how does this algorithm work? It has these A messages and the B messages. The A messages go down to all the nodes in this graph tree, and then the B's come back up. And the path going back up is determined by the parent node. Okay, when I receive an A, my parent will be that one. But the first A I receive sets my parent. That means if you adjust the A's to be fast or slow, you can create a path of parent nodes. And the B nodes have to follow that path. You got that much, right? You got at least to there. So the trick is you have to then choose speeds for the A nodes so that the B nodes will take longer paths when the A nodes go faster, right? That's not so hard, right? So here, let me do a simple example. Let's say there's n over 3 nodes going down. Let me call this node n over 3. So n is some big number. I'm not going to draw it. So this is like a bunch of nodes going down. And here on the other side is 2n over 3 going here. Okay. So if the messages all take 1, then the fastest path will, when these two goes down, the P node will receive first from the left side, right? So the table will take n over 3, go down, the A's go down, and then the B's will go back up this way. So this one will be n over 3 plus n over 3, right? 2n over 3. Notice that this is not going to go worse because of this one. Now let's say we do 0 or 1. Now I can trick the algorithm to make it go slower. I can choose some of the messages going down here to be 0. All these will still take 1. So I can choose them so that the time will be a little bit less than n over 3. Okay, so some of these will be zeros. So it'll be less than n over 3, minus some small number, epsilon. That means the fastest will be this way, right? That means the link going back will be n over 3. The links going back will be going this way, so 2n over 3. So it's around n. Okay? So this is slower than that, right? So it's not so hard, right? Is that right? Am I telling something reasonable here? Okay. Wasn't so hard, right? Okay, good. You just have to have clear thinking. And today we're going to do some more clear thinking. Okay. So that's all I want to say about complexity. Just wanted to come back on that part that we started. Today we're going to talk about failure detectors, but before we do that, I want to talk about a part that we didn't do yet from the programming. Remember when we write the code, we wrote some code last time, huh? We wrote some code. Here's the code that we wrote for perfect links, for example, using this nice event concurrent model where you wait on some event, which could be a message, and then this piece is executed. This is all sequential, okay? But these separate blocks will all kind of wait, and they will fire when something appears. And so you have kind of a very nice interleaved execution, okay? Now, the algorithms, we're going to write lots of algorithms, and the algorithms will be different depending on what kind of model they run on, okay? If we have synchronous model, or asynchronous model, or partially synchronous model, that will really change a lot the algorithms, okay? So whenever you write an algorithm, you have to tell me, is it for synchronous machine, for asynchronous, or whatever, huh? If you don't tell me that, then it's not complete, the specification. We have three kinds of systems. I mentioned already these two, asynchronous, synchronous, but today I'm going to give you the formal definition of partially synchronous. Okay, so the first one is asynchronous. This one is in some sense the simplest one. There's no timing assumption, no upper bounds. Processing time can be any arbitrary finite time. Transmission of a message can be any finite time. It could make 10 years or 2 milliseconds, whatever. And this is what the formal model defines by default. Okay? Remember the deliver events, which you can make wait as long as you want. And the only thing we know is causality. Okay? Which is basically the order between events. There's no hardware clock in this model. Adding a hardware clock would be a very different new kind of other assumption. So there's no hardware clock. All you know is causality. Okay, you cannot print out the space-time diagram because all of the ones that are equivalent, you would see the same configuration. This is the computation theorem. Okay, and we talked a little bit before. So this kind of system is very easy to define. It's very easy to implement. We make really no assumptions. So the question is the internet like this? We already talked a little bit about that. Huh? Is the internet asynchronous? Because you don't really know how long the message takes, right? On the internet. I connect to a server, and it could take 1 millisecond, could take 10 or 100, sometimes even longer. So it doesn't really seem like there's a bound. If you look at TCP, there's no numbers built in there. It all depends on how things are wired together, on how it goes through the routers. So the internet is kind of implemented with no bounds. So is it really truly asynchronous? It's kind of important, because if it were truly asynchronous, that really there was no bound, then we would be stuck, okay? Then we would have a hard time writing programs on the internet. Luckily, physics is helping us, okay? The other extreme is synchronous. Here we have known upper bounds. We know that the node processing will always be less than 1 millisecond before it sends a message, and the message transition delay will be guaranteed less than 10 milliseconds on local area network or something like that, okay? And typically they will even have synchronized clocks, actual clocks, and you know how these clocks are related to each other. This is all possible because of these known upper bounds. Okay, so this kind of system is really nice for writing algorithms, but they're very hard to implement, really. And if you make the system very big, you already will make it harder and harder. A synchronous system could be like a small cluster. The physical distance is very important. If I have a 10 microsecond delay upper bound, then the nodes have to be very close together. Light does not go very far in 10 microseconds, okay, or even less. So, and there's all kinds of other overheads. In wires, the signals are even go slower, and in transistors, they even slow down more, and there can be capacitance and so on, even slowing things down even more. So a synchronous system has to be physically very small. Making a large synchronous system is really hard, expensive, or impossible, okay? So it's clear the internet cannot be synchronous. So why do we study synchronous systems? So we're kind of in a bind here. The asynchronous systems, they are easy to implement, but it's hard to make algorithms. And here, the synchronous systems, the algorithms are easy, but they're kind of very hard to implement unless they're very small. This multi-core system is synchronous, fine, but a network with nodes that are maybe a kilometer apart, it's not really going to be synchronous anymore. So why do we study them even? If they're not practical, and clearly the internet is not this. So why even study them? Why am I even mentioning them if they're not really that, if they're very expensive and the internet is not this? Why am I mentioning them? Because I'm a nasty theoretician. No, I'm not a theoretician. Why mention them? Well, it's an extreme case. So theoretically, it's already interesting. Because it's an extreme. Once you know the two extremes, it's interesting to see what are really the limits for such an extreme case. And they do exist. Small, very fast machines are going to be synchronous, like GPUs are going to be synchronous, for example. But clearly, the internet is not like that, okay? So now we get to partial synchrony, and this was a new concept that was invented, okay, in the, not sure exactly when, around the 1990s, I think. And formally, it's a system that changes. It's when you start running your algorithm, it's asynchronous, which means there are no bounds, and eventually, which means after a finite time, the bounds will exist. Now, the interesting thing is, you don't know how long that's going to take. All you know is that it will happen in finite time. And you also don't know what are the bounds. All you know is that they will exist. It's a very interesting combination of knowing and not knowing. A very interesting exercise in vagueness, right? But in fact, it's a very good definition for several reasons. First of all, here in blue is kind of an intuition. When I run an algorithm, I want my algorithm to run synchronous, okay? Because then it's easy. Well, if I run it long enough, then the system will be synchronous. So the algorithm just has to run long enough. How long? Well, whatever it takes, and then it will work, okay? So are there such systems? So this is a very interesting kind of definition, It's a combination of vagueness and precision, See that? So after some finite time, which you don't know how much, the asynchronous system, which has no bounds, will become synchronous. So bounds will exist, but you don't know them. But you don't know their values, okay? So in fact, clearly there are such systems, but there's a very famous one. So the internet is a partially synchronous system because of physics. because of locality. When I talk between two nodes, there will be a bound, which depends on the physical distance. But if there's a problem with the routers and the message has to make some weird detour, it takes longer, then it will basically be executing in a larger space. But that will mean just that there's a new bound, which is higher. So there is always a bound, actually, okay? Depending on how far the messages have to go. There will always be a bound, and whenever you run an algorithm, it will run in some finite space. So it will have a bound, okay? So this actually works for the internet, okay? So here's a diagram. The algorithm starts, here it's asynchronous. At some time, who knows, but sometime, it becomes synchronous. So from this point onwards, the system is actually synchronous with upper bounds. And so the algorithm, it just has to make sure that during this period, it doesn't do something stupid, okay? Because eventually, during this period, it will be able to do its work, okay? So it's a very interesting constraint when you write algorithms, okay? See that? Okay, so that's all for partial synchrony. And now we can go to failure detectors, which is another great invention of the 90s. So you see, the 90s was a good time for distributed systems, huh? Okay, so in the 80s, the 1980s, distributed systems as a discipline was completely a mess. And then it slowly got cleaned up. Leslie Lamport invented the consensus algorithm on a partially synchronous system. That was around 1990. So that simplified things already. People started understanding that partially synchronous systems were a good idea. But it was still not enough. Algorithms were still a mess until the second concept was invented, which is failure detectors. Okay? So failure detectors, basically, an algorithm runs on a system, it has to worry about the timing. About messages taking time and how maybe we have to time out. And so you have to program that. Timing assumptions. You have to program things, heartbeats, timeouts, and it's all over the place. So if you have to program it in every algorithm, it really makes your algorithm a mess. And in the 90s, algorithms were kind of a mess. If you look at the research articles of those days, until a guy by the name of Sam Tuek, so not Leslie Lamport this time, invented the concept of failure detectors. And it's an abstraction. It's a black box. And it tells you what it thinks. It says, I think this node has failed. Or maybe not. Okay? And it sometimes can make mistakes. Or maybe it doesn't make mistakes. So it all depends on what model it's using. Okay? So this was a major step. This, I guess, was also around 1990. So 1990 was kind of but it took several years after that before everything was cleaned up. So failure detectors are kind of like this. This yellow box, remember, is like our code, the code we write. We have something running in there, and messages come out of it. That's it. So this thing is running, and every once in a while, it sends a message out. We don't know when. And depending on what kind of failure detector, this message means something. Okay? This is failure detector P. It's called failure detector P. All distributed system people know what failure detector P is. It's the best possible failure detector. It never makes a mistake. If it tells you that node PI has crashed, you can be guaranteed it's going to be correct. Node PI has crashed, okay, if it sends a crash message. So this is the perfect one, but the problem is you need a synchronous system to implement it. Okay, so we have this other one here, And this symbol, this diamond symbol, means eventually, comes from temporal logic. If you follow a course on model checking, you will understand. Temporal logic tells you about things that happen over time steps. So this one is called eventually P. Okay, eventually perfect. And this is the one we can implement on a partially synchronous system. This one sends two kinds of messages, suspect and restore messages. If it suspects a node to be failed, it will send a suspect message. But maybe it makes a mistake. So if it thinks, actually P1 did not fail, then it will send a restore message later. Okay? So it starts out by making mistakes. It can make mistakes, this one. But because it's running on a partially synchronous system, it starts out making mistakes, but eventually, I really like that word, eventually, it never makes mistakes anymore. When is that? We don't know. But we know that after some time, it's going to be always correct. There exists some finite time, and that this one will be always correct. And before that time, it can make mistakes. Okay? This is the eventually perfect. So this is the one you can implement on the internet. This is the one we're going to use a lot. Okay? So this is going to be a biggie in the course. Okay? So we're going to show you how to implement. There's many ways to implement them. They're kind of black boxes, or yellow boxes, but there's code running in there. So we're going to implement them, and typically nodes will exchange messages. And these are called heartbeats because they're periodic. And I send a heartbeat from 1 to 2, I get a heartbeat back, and if I don't get anything back, I can time out. If I do a timeout, then I suspect that guy, maybe he's failed. But if I get the message just a little bit late, then I will revise the suspicion and say, actually, maybe the message is just taking long, okay? Okay, so that's kind of how it works. And we're going to spend a big part of today trying to really understand these two things, P and eventually P, okay? So these are two important things, concepts. We're going to, first of all, specify them formally. And there's two kinds of requirements for failure detectors. There's completeness. Completeness means it doesn't actually miss any crashed nodes. It will actually detect if a node crashes, it will not forget it. So it's complete in that sense, okay? And the other property, which is kind of the opposite, is that it will not, that it will actually not make mistakes. It can actually suspect a live node. So a node that's not crashed, it might be suspected, and that's a mistake. So that's not accurate. So these are the two kinds of properties. You don't miss any nodes. It might take some time, but you eventually get them all. It's kind of like the Pokemon requirement. Gotta catch them all or something like that. So that's completeness. But accuracy means you don't make a mistake. If you catch one, then it's really a Pokemon that you caught and not something else. Okay? So there's no mistake. So those are the two kinds of properties. Okay? Now, remember our discussion on safety and liveness. So there's, of course, a trivial way to get one or the other. For example, completeness. How do I get completeness? What's the trivial way? If I just want to get completeness.
Just tell that they all crashed.
Say that everybody has crashed. I won't miss any. But what about if I just want to do accuracy? I don't want to ever make a mistake. A mistake in the sense of I'm unjustly accusing a live node of being dead. Okay? How do I avoid such mistakes? It's the opposite, huh? Yeah?
And you accuse no one.
Just say everybody's always alive, even if they're dead. Okay? So the problem, of course, is getting both of them. Huh? That's always the problem with safety and liveness. The trick is making sure you satisfy both and not just one. Huh? Okay. So we're going to extend our formal model with this. So these failure detectors are kind of like oracles. They're magic boxes, and they will be giving us information. And so for the formal model, they're just extra information coming in. Okay? So each node will have an extra state, which is the failure detector state. Okay? Which can be updated. Okay? So every node will have automatically this information coming from the failure detector. Now, I mentioned completeness and accuracy. There's actually different levels. You can be very, very demanding, or you can be kind of not so demanding. So we can say strong completeness is basically the strongest thing, is that every crash node is guaranteed to be eventually detected by all correct nodes. That means all the correct nodes, every single one, a correct one which is one that does not crash, every single one will eventually detect every crash node. That property is called strong completeness. There exists a time after which all crash nodes are detected by meaning you've noticed that they failed, by all correct nodes. And we will only really look at detectors with this property, actually. Okay? So, is this a realistic property? What do you think? Is it realistic? Is strong completeness something that you can actually get? Is it a realistic thing in a real system? What do you think? Is it nasty or is it nice, strong completeness? Is it easy to get? It's pretty easy, huh? No? You will, if a node crashes, no messages will come from that node. So every node will notice that, okay? So strong completeness is not the hardest one, We have another one called weak completeness. Sometimes it's not possible to get strong completeness. Weak completeness means every crash node will eventually be detected by some correct node. There is some node, which is like a privileged node, that can see all the crashes, okay? It can see all the crashes. Some node can see everything. And the intuition on this, it's important to get good intuition. The intuition on this is something called, you know, have you ever heard of this? A panopticon. You know what a panopticon is? You can look it up on Wikipedia. A panopticon is a weird kind of invention. It's a prism. It's a prism, which is like a cylinder, okay? And you have all these prison cells around here. Let's say this is a little rectangle of prison cells. And you have one guy standing in the middle, who can see all of them. And the person in the cell, and the cells have glass wall on one side. So when you're a prisoner, you don't know if the guy's looking at you, but he could be looking at you anytime. So you're going to be careful, right? Because supposedly he could be looking at you anytime. So this one guy has a privileged view. If you're sleeping, he's going to see it, okay? So this guy actually is like weak completeness. He's the privileged node with the good view of the others. Because the prisoners cannot look at each other, okay? But this guy can see everything. Okay, so it's kind of like a panopticon. Or another thing is it's like a football game. The players can see all the people in the bleachers, all the supporters. And if there's a supporter falling asleep, the player can potentially see that if he has good eyesight. So the players are kind of privileged now. So that's another kind of example, okay? So weak, strong completeness, everybody sees the crashes. Weak completeness, some privileged node sees the crashes. Okay? And then, now let's go to accuracy. So accuracy is about mistakes. Never make mistakes. And the best kind of accuracy is strong accuracy, which means you never suspect a correct node. That means if a node is alive, you will never make like an unjust accusation. Okay? P does not suspect Q unless Q has actually crashed. So what about this one? Is this a realistic property? What do you think? I mean, strong completeness was pretty easy to satisfy. What about strong accuracy? Can we get it? How do you get it? How do we get it? How can we get it on the internet, for example? It means if I'm looking at some Japanese guy who's very far away, and then I can tell whether that guy, his computer has crashed or not, for sure. Never make a mistake. Is that reasonable? What do you think? Yeah?
Well, to me, it's not realistic because we might have a good link, a link which was good before, but then we suffer a failure.
Right.
So it is rerouted.
Right.
It takes, let's say, double the time that we expected it to take the previous time, and then we suspect it because we think it's crashed, but then we know it hasn't crashed, and then we will augment the time we wait. But at the
so we
first time
suspect it because there's some problem with the network. Yeah, like you said, so it has to go through another router, and so we suspect it because it's kind of timing out, but it never crashed. So, I mean, you're absolutely right. This property is not easy to get. You basically need a synchronous system to get it. You really need to have a strong upper bound. Whereas, like on the internet, you don't have that. Okay? You can always get timeout, and this thing is still alive. So, strong accuracy is a very hard and strong assumption that's hard to get. And somehow it's related to P, okay? This perfect failure detector, which is very hard to achieve, okay? So we have another one, then, called weak accuracy, which might be easier. Again, we have some kind of a privileged node here, which is not crashing, and everybody sees it. So it's kind of like the opposite of weak completeness, It's like the player on the football field who's running around. He's not sleeping. He would not be able to make a goal if he was sleeping. But you see he's not sleeping. You can verify. There exists a correct node, and all the supporters can see that. Okay? There exists a correct node, and nobody will suspect it. That is actually much easier. You have some kind of a privileged node. That is always seen, okay? And nobody will ever make a mistake with respect to that one. But it's still kind of strong. I mean, it's weaker than strong accuracy, but still you have to actually see this guy, and he might be far away, okay? Okay. We can make the property, we can make these properties eventual. Let's see, did I? Weak and strong accuracy. Strong accuracy means you never make mistakes. But that's a little bit too strong. So we can make it a little weaker in another way. We can say, after some time, it's strong. It's called eventual strong accuracy. That means it's allowed to make mistakes for a while, but after some time, which we don't know, but it's finite, then it will make no more mistakes, okay? Or eventual weak accuracy. After some finite time, there's one node that everybody can see, okay? After some time, the requirements are fulfilled. Before that, the node can just do any old weird thing, Okay, so these assumptions are much weaker, okay? these assumptions are much weaker, and in fact they kind of connect to partially synchronous systems. Okay? Okay, so let me make a summary now. We're going to be writing lots of algorithms in this course, and these algorithms will be using failure detectors. Okay? And the ones that we will use are these. Okay? The main detectors. Remember, in the 1990s, people were inventing lots of stuff, so there's lots of detectors that people invented in those days that are really not so much used. But these are the ones that are the good ones that are left over that we will use today. And the main ones are perfect and eventually perfect, P and eventually P. The perfect, there's also the ones called strong. Why is it called strong? Because the guy who invented it called it strong, okay, and the name stuck. So there's a strong detector and an eventually strong detector. And what's the difference? The difference is that it's only with respect to one node. Weak accuracy means that there's one like privileged node. Weak accuracy is like one privileged node. So the strong detector only is strong with respect to one node, actually. Okay? And eventually strong starts out being anything, and eventually, after some time, it's weakly accurate. Okay? So these detectors, this one is actually the strongest one is perfect. Now, this is basically the strongest one. This one's a little bit weaker, actually. Eventually perfect is also weaker, but in a different way. The strong is weaker in terms of which nodes it's looking at, but eventually is weaker in terms of time. Okay, after some time, it becomes perfect. And the weakest one on this slide is the eventually strong detector. Okay, and for internet, partially synchronous, these are the two guys that we want. Okay, notice all of these are strong complete. That means every correct node will see every crash eventually. That means everybody sees the crashes. And that is very reasonable. Okay? Now, there's also 4 other ones. I'm just going to mention them, but we're not going to be really using them. These are the weak completeness ones. Okay? These are the ones where the completeness is only with respect to one node. So that there's basically one node that can see all the crashes. And people were worrying about these. These are systems where you have like privileged nodes. And you have detector Q. It's called detector Q. You have the weak detector. This one's called detector W. Then you have the eventually detector Q, which is eventually Q. And you have the eventually weak. Okay. Why did they pick these weird letters, Q and W? You beats me. It's just that the guy inventing them picked those letters. Okay, so you have Q, W, eventually Q. So that gives us 8. Okay, but in fact, out of those 8, by far the most important ones are P and eventually P, and a little bit still used are strong and eventually strong. That's it. The other 4 are basically not used. I mentioned them just in case so that you have a complete view of what people were talking about. Okay? Okay, let's talk now about these 2 guys, P and eventually P. And as usual, we have to give them an interface. We have to give them properties. Safety and liveness, and we can actually show some kind of implementation, maybe. Depends on that, depends on the hardware. So the interface is very simple. For P, it has only one thing, which is an indication. Remember, an indication is a message that goes up, comes out, which is crash PI, telling me that node PI has crashed. And it has these 2 properties, strong completeness and strong accuracy. Okay? So it has these 2 properties. So like we did last week, I'm going to discuss always a little bit these properties, because the actual precise definition is very important here. Okay, strong completeness says, eventually every node that crashes is permanently detected, by every correct node. Okay, so the nodes will all see all the crashes. And strong accuracy says, if a node is detected, then it actually has crashed. So there's no mistake. Okay? It will not unjustly accuse a node of being crashed. Okay, now we remember safety and liveness. So the first one, is it safety or liveness? You tell me. P of D1, safety or liveness? Someone over there. Safety or liveness? Because I've heard a lot of good things coming from here, this part of the room, but I want to hear stuff from that part too. Safety or liveness? P of D1. You tell me. Somebody has to tell me. It's easy, huh? Come on, you guys. This is very easy, okay?
Liveness.
Liveness, okay. Why is it liveness?
Eventually, usually, is often with liveness.
Yeah, eventually, yeah, something good happens. Yeah, so it's liveness, okay. That's acceptable, liveness. So probably the other one will be safety, because you need both, huh? But this is easy to see that it's safety, huh? How can you break the system? A safety, you can break the system, huh? How can you break it?
Detect a node that didn't crash.
Exactly. You detect a node and it actually has not crashed. That's a mistake, and the system is broken if you do that. So that's the safety, yeah? Okay? So the implementation, it can be implemented in a synchronous system. And then the implementation is easy. You can't really implement it in other kind of system, right? It just doesn't work. But in a synchronous system, you can do it. And the idea is you have some upper bound. So we assume the messages take between 0 and delta, time units, not seconds. And you send heartbeats. Every gamma units, you send a message to all nodes. So all the code, the nodes execute this code. Huh? So it has like an infinite loop. Every gamma time unit sends a heartbeat. And then it waits. After it sends, it waits gamma plus delta. Okay? If it did not get a heartbeat from PI in a period of gamma plus delta, then it knows PI has crashed. Okay? And that's it. And we can prove that this is correct, that it satisfies the properties. Okay? Okay, so let's prove the two properties. So the accuracy is a little bit harder, but the completeness is very easy. If the node crashes, it won't send a heartbeat. And if it doesn't send a heartbeat, then it can't the other ones cannot receive it. So they will all see the crash. Okay, so that's easy. Strong accuracy is slightly harder. So assuming local computation doesn't take any time, the maximum time between two heartbeats, notice PI is sending heartbeats, huh? Every gamma, but the messages take time. So the maximum time between two heartbeats is gamma plus delta. If this one takes 0 time, and this one takes maximum time, so this is the maximum that it can take. So if I receive a heartbeat here, then if I wait gamma plus delta, I must receive another one because of the upper bound. Huh? If PI is alive, then I must receive it in this time. And if I don't, then I'm absolutely sure PI is dead because of the synchronous network. Huh? Okay? So that's it. That's the proof. It's a very easy proof. Huh? I'm not formalizing it more than that. Okay, now let's go to the more interesting one, which is the eventually perfect failure detector. This one has a slightly more involved interface. It has 2 possible indications. Suspect PI and restore PI. So I'm never sure, so I can suspect. So this guy is very suspicious of other nodes. Huh? It suspects PI, but he's actually nice. If he realizes that he made a mistake, then he will take it back. I'm sorry, I didn't really mean it, and he will do a restore. Okay? And this one also has 2 properties. strong completeness, but eventual strong accuracy. Eventually, no correct node is suspected by any correct node. You can see how important to the word eventually is, huh? Okay, we can implement it on top of a partially synchronous system. So this is our first algorithm, actually. You can see how we implement algorithms when we don't know when the bounds exist. Okay, so how does it work? Again, every node will send heartbeat, every gamma, time units, to all other nodes, and every node will wait. But this time, it's not a constant. It waits a certain time, but that can change. So it waits t time units. If it does not get a heartbeat from pi in that time, it will suspect pi. If it's not already suspected, and put it in the suspected set, so you don't repeat suspect messages. Okay, only once. So that's nice. But maybe the t was just too short. Okay, so if it does get a heartbeat from pi after that, and pi isn't suspected, that means it has previously suspected it, then it says, oh, I made a mistake. So it indicates restore, removes pi from suspected, and increases the timeout t. It says, clearly t was too short, too small, I have to increase it. Okay, so that maybe the next time around, it's better. Okay, and that's it. Okay, this increase has to satisfy a certain property. Yeah? If you increase repeatedly, the timeout has to become greater than any fixed bound. You cannot, so Zeno the philosopher could be very smart and you're only increasing the timeout, but always a little smaller amount. No. You have to increase it so that it eventually will get bigger than any finite number. Okay, so how do we prove it? So strong completeness is like before. It means we didn't get the heartbeat, the node. The node actually has crashed, so we will not get heartbeats. So we will suspect to the node if it crashes. Okay. If it really did crash, that's not a mistake. But now the eventual strong accuracy. And the idea is that it starts by making mistakes, but after some time it makes no more mistakes. So let's say P is inaccurately suspected by a correct Q. So Q thinks that P has crashed, but P has not crashed. The timeout T increases, and now there's two conditions that happen. First of all, so this keeps going. Eventually, the system becomes synchronous, condition number one. That means bounds exist. And second condition, eventually T becomes larger than the unknown bound, whatever it is. T will keep increasing. Eventually it will become larger than the unknown bound. We don't actually have to know the value. Eventually it will become larger. So you need these two conditions, but they will both arrive in finite time. Eventually the bound will exist, delta, and eventually, once it exists, T will become greater than that bound. Starting from that point, Q will never make mistake with respect to P anymore. It will receive the heartbeat less than in the time bound, and it will never suspect P again. That's very nice, okay? So you see, it works because of these two conditions. There's two conditions here. Okay. So we actually made a simple algorithm using partially synchronous. Of course, it's not always going to be so simple, but in the rest of the course, we're always going to use eventually P. We're going to use, it's going to be like a primitive, and so we'll never actually have to implement it anymore. And actually, you can make it smarter. You can actually look at a real system and reduce the mistakes. Of course, you can never really get rid of them. That would be like magic. But usually the mistakes, they will have some issues. They will make the algorithm less efficient if there's lots of mistakes. So it's usually a good idea to make less mistakes. But of course, the algorithm has to work no matter how many mistakes there are. Huh? Where I'm talking efficiency might change, but the correctness will not change. Okay, so let me make a small break, and then we'll start doing some specification engineering. We'll see how to adjust. We'll try to make an algorithm with a good specification. And it's actually a nice algorithm. It's called leader election. Okay, but let me make a small break first. To play around with specifications. Remember we had properties, the properties, and then we have code. And here we have safety and liveness, and here we have these blocks of code. And there's kind of a connection between the two, of course, because the code has to satisfy the properties. But in real system design, you can change both of them. So maybe we add a property to make the code simpler or nicer, or to make the behavior nicer or something, okay? So this is an example of that. Let me show you an algorithm called leader election. It's actually an interesting algorithm. Leader election, it's usually called LE. You have a bunch of nodes and they have to elect a leader. And the reason why I'm showing you is that it actually is kind of like failure detection, okay? Sort of, intuitively. Failure detection will detect failed nodes, but leader detection will somehow do something similar. All the nodes will kind of elect a leader, a single node. All the nodes will agree this guy is our leader, okay? And it has to be correct leader. And it's the same one for everyone. So in some sense, in some vague sense, it's kind of like failure detection, okay, in a weird way. And because it's important to understand these kind of connections, okay? Leader election will always suspect all nodes except for one, the leader. It means all the other nodes are non-leaders, okay? Failure detector, you will have failed nodes. In leader election, you'll have non-leader nodes, okay? So one node is taken as the leader, and there's some properties regarding that node. Like everybody has to have the same leader, okay? And so we're going to look at that. And actually there's two algorithms. There's leader election, which is kind of similar in some ways to P, perfect failure detector. So there's some kind of intuitive connection between the two, but we can also make it eventual. We can make anything eventual. There's an eventual leader election, which means that we don't immediately get the leader without mistakes, but eventually we will. This one actually has a name because this algorithm is kind of a standard thing. This one is called Big Omega. This is a Greek letter omega. Huh? So this one is called Big Omega. It's not called eventually LE with an eventually symbol. So it's called omega, Big Omega. Okay. See a lot of historical funny names in distributed systems. Okay. So we'll start with leader election. And I match them. I'll somehow show you how it corresponds to P. There's some kind of intuitive connection there. Remember P is perfect, huh? This guy is the perfection incarnated. Always eventually detects failures. And notice completeness has to be eventually. You can't instantaneously see when a node fails, but it will always detect it. And it will never suspect a correct node. Strong accuracy. Okay? Now, leader election is has kind of similarities to that. Okay? So it's always complete. Complete means every correct node will have some leader. That's kind of a completeness property, yeah? If the leader crashes, it'll pick another leader. So the leader has to be correct. Notice that nodes can be crashing here. These algorithms are fault tolerant. Leader election is a fault tolerant algorithm. Nodes can crash. So if I think node X is the leader and X crashes, then I will change leaders, okay? But I will eventually trust some correct node. So in that sense, it's complete, okay? But it's also accurate. So I will never, when I pick a good leader, I will not abandon that leader. No two correct nodes will trust different correct nodes. Because if that was true, then there would not be one leader. And one of them would have to change, so one of them is like making a mistake. Okay? So that's like an accuracy property, yeah? If two nodes trust different correct nodes, then one of them has to be making a mistake here, because we have this perfect leader election. So one of them actually has to change the mistake, okay? So we're kind of, what I'm trying to do here is kind of come up with a nice specification for this, okay? So, for example, here we have two properties, okay? Eventually, every correct node trusts some correct node. So eventually, I will pick a leader, okay? Trust is like the leader, I will pick a leader. And no two correct nodes will trust different correct nodes. That means two different nodes will never pick different leaders. That's like saying there is only one leader, There's also a famous film where they say there can only be one, Remember that? If you have some culture. So it's like that. So two different nodes will have to have the same leader. So, okay, so we can start with these two properties. But somehow these are maybe not good enough, okay? We're doing specification engineering. If we just have these two, it might seem it's perfectly good. And it is good, actually. But maybe the behavior of the system might be weird, even though it's satisfying those two properties. And here's an example. So this is a time-space diagram with three nodes, P1, P2, P3. They all elect P3 as their leader, but P3 crashes. That means they have to change, of course. Since we have perfection, they're both going to know that. So P1 will elect P1. Okay, fine. But P2 is very slow here, very slow. It's not doing anything here. So P1 can change and elect P2. See, that's okay, because here we have two correct nodes trust different correct nodes. Well, here there's only one node trusting a different correct node here, 1 and 2. 2 has not done anything yet, because P3 is crashed. You see that? So as long as P2 is not doing anything, P1 can be kind of wishy-washy and switch left and right, So maybe we don't like that. The fact that this specification will allow kind of funny, switchy behavior here, okay? It's correct, It will be, this is correct according to this, but maybe we don't like that. So we want to stop that. We want to disallow P1 doing this funny, switchy behavior. And that means we're going to do some specification engineering. So I'm going to add a property, a third property, that will kind of make this be forbidden, okay? So I say it's inaccuracy. It's not really inaccuracy. I put it in quotes. Because technically it's not really making a mistake, but it is being wishy-washy. So let's stamp our foot down on that and add another property that avoids this wishy-washy behavior. And I'll add a third property called local accuracy. And this property says, if a node is elected leader by PI, all previously elected leaders by PI have crashed. That means once PI picks a leader, it's not allowed to change unless there's a crash there, okay? So if P1 elects P1 as the leader, okay, then it cannot change to P2 because P1 has not crashed. It can only change if there's been a real crash, so it's like really justified. Okay? So with this extra property, we kind of stamp out this funny behavior that we don't like. Okay? So you see, we don't really need that in some sense, but we add it just so to stamp out kind of funny behavior that we didn't like. Okay? This is specification engineering, is tweaking the specification. Okay? So that means the interface is like this. We have only one indication, so that's like a failure detector. LE leader, leader elect. The leader is PI, that's it. It's like the crash messages, it just tells me leader is, PI is the leader, and that's it. And we have these three properties. Eventually, every correct node trusts some correct node. That means we will eventually elect a leader. Every node will elect a leader. No two correct nodes trust different correct nodes. That means two nodes will never have different leaders that are correct. And the third one is the one we added just so that the algorithm doesn't change kind of frivolously of leader. If a node is elected leader, all previous elected leaders by that node have crashed. That one will avoid these frivolous changes. Okay? And so we've kind of added this third property to kind of tweak this behavior. You see that? And it's very similar to perfect failure detector. This one will never make any mistakes. And there's only one indication coming out there. Okay? So it kind of resembles P. Okay? But we've added this third property to make it more kind of the way we want it to be. And now I write the code for this. So the code is very simple. And the way to do that is, it's very easy. I rank all the nodes. So to make it very simple, I assume that the nodes have some ranking. Like every node has some kind of ID, and they're kind of numbers, and they're in some order, okay? Like P1 has a higher rank than P2, and so on. It could be whatever, the MAC address or IP address in real life. But there is some ranking. There's some order. And that makes electing a leader easier, okay? We have this function R, which tells me who are the nodes that are higher ranked than me. So R of P1 is empty set because P1 is the highest. R of P2 is P1. Okay, so P1 is higher ranked than me. So this function will tell me who are the higher ranked. So I'm assuming this function exists. Why can I assume that? Well, because I'm writing the pseudocode and I'm the master of the language. So I'm just adding this because I think this is good for my pseudocode, okay? This function. And the code then becomes very simple. This is the whole code. So there's only like 5 lines of code here. Right? All this discussion with these properties and subtleties and everything, and then you get this very simple code. That's actually very common. That's going to be very common in this course. The code is like very dense somehow. So the leader election here uses a perfect failure detector. We're assuming that we have this box here, perfect failure detector, and the leader election is built on top. And we have 3 pieces of code. First of all, the init, we'll just do initialization. Okay? First of all, I have this set suspected, which starts out being empty. I take as the leader the highest rank node. That's it. The leader is the highest ranked node. It's so simple. And I send a message saying, this is the leader. That's it. But now the rest of the code is there because of crashes. So if there were no crashes, this would be it. But our code is fault tolerant. And there's 2 things that can happen. First of all, the perfect failure detector will send us this crash message. And we just add it to the suspected list, okay? Or set. So the suspected set is just telling us all the nodes that crashed. Okay? And then the problem is, this guy, who we thought was the leader, maybe the guy has crashed, and then we need another leader, okay? So if there exists a PI, such that all the higher ranked nodes are crashed, they're a subset of suspected. So the way to read this formula is all the higher ranked nodes than PI are crashed, and PI has not crashed, then PI is the new leader. Ta-da! Very simple. Okay? So basically, you pick the highest ranked node as a leader, and if that node crashes, you pick the next one, and so forth. So this is a completely fault-tolerant leader election. You see how simple it is, huh? Using failure detector, and if we can rank nodes, this is the whole code. This is a full fault-tolerant leader election. Okay, but the problem, there's still a problem, it relies on P. And P is very hard to get. These elusive perfect failure detector, okay? And so the next step is I will show you the other one, which is omega. LE is perfect, never makes mistakes. But that's kind of not realistic. Let's go to another version of the leader election, which is allowed to make mistakes in the beginning. And it's the same analogy. We go, it's like from P to eventually P. So eventually P will be weaker than PE because it's only eventual accuracy. So accuracy is mistakes. That means it's allowed to make mistakes for some time. And so we're going to do the same with leader election. We're going to allow in omega that the leader election will pick the wrong leader, but only for some time, but eventually it will be good. Okay? And so here are the properties of leader election. So we forget this third one now, because eventually he's going to be in any case making mistakes. This was kind of to make it less frivolous, but the omega is going to be making real mistakes. Okay, that's part of the deal for omega. So we drop this third property, and the second one, the agreement, we will make it eventual. Okay, we'll make it eventual. Okay, so we get this interface. This is interface of omega. Notice here we have again one indication. Pi is the leader. Notice here we have two properties now, not three. And this one is eventually no two correct nodes, trust different correct nodes. And so in the beginning, we're allowed to have two nodes thinking that the leaders are different nodes. But eventually, that will not work anymore. Okay? And we're going to write the code of omega depending directly on eventually P. Okay? The same way that LE is written based on P, omega will be written based on eventually P. Okay? And it's actually very simple code again. Every node will trust the highest ranked node among the nodes not suspected by eventually P. Even though P it makes a mistake, this might be wrong, there might be mistakes in here, but that's not a problem, because eventually there will be no more mistakes in there, and then everybody will see the same crashed nodes, no more mistakes, and then you will have only one correct process, which is the highest one. And here's the full implementation. This is the whole code of eventual leader election based on eventually perfect failure detector. It's just one page, just one extra line compared to the previous one, because instead of crash, we now have suspect and restore. Suspect will add PI to the set, but restore removes it. So the suspected set in the LE is only growing. It's never getting smaller. Whereas here, the suspected set can be growing and getting small, shrinking, okay? But all we know is that eventually it's correct, but in the beginning it might go do all weird stuff. And here we have, if all higher ranked nodes are failed, and PI is not failed or suspected, then PI is the leader. But this might be wrong in the beginning. You see that this suspected set might be wrong, but eventually it's not wrong. Okay? So basically, the weirdness of partially synchronous, that you can make mistakes, is kind of lifted up here into the weirdness of eventual leader election, which also can make mistakes. Okay? So you see that? So this is typically the way we're going to be writing algorithms. Okay? So this is actually a nice algorithm because it's fault tolerant and it runs on a partially synchronous system. Okay? And it's concurrent, of course. This is running on all nodes. It's concurrent, fault tolerant, distributed algorithm running correctly on a partially synchronous system. And it's one page of code. That's not bad, huh? You see that? That kind of a strong algorithm, it's only one page of code. Well, you tell me, yeah, sure, because you've defined everything so that it's simple. Yes, exactly. If I define everything in the right way, then life is simple, okay? So you can start to see the power of the model, of the programming model, and we'll see more and more later, of course, Okay, let me do another variation. Let me now go and grab our good buddy crash recovery, which is kind of a nasty failure mode. Crash stop is easy, The node just stops doing stuff. But crash recovery, it has some stable storage and it can reboot and keep going. What if we want to do leader election for crash recovery? How do we do that? Because what can happen for crash recovery? It can crash and it reboots. But then it can crash again and reboot again. But it can't do that forever, What did we say? Remember, there's something about crash recovery. It can't just crash and reboot forever. Why not? Why is that really not a good idea? Because it could crash and reboot once, twice, 3 times, but not forever. There's something not good about that one. Why not? You just remember what we were crash recovery? Because that's not, if it is crashing all the time and then recovering, but crashing just after, it's not stable, okay? Then there's still something wrong, and so we don't like that, okay? We cannot elect a recovered node if it's unstable. It's always crashing and recovering. And the way to fix that is count the number of times it's crashed. That's a funny thing, The node knows how many times it's crashed. And it's the epoch. This is called the epoch. And this is a very common technique where the algorithms divide the time into epochs, where some major thing happens to go from one epoch to the next. So you count the epochs. And you will elect a leader that's not just the one with the highest rank, but it also has to have the lowest epoch. So the node that is always crashing will not be elected, okay? Because there's always going to be someone with a lower epoch, okay? And so you have this extra epoch thing that counts the number of recoveries, okay, which has to be piggybacked and so on. And you keep track of the leader. You store it in the state. So you have to be using the stable storage. So you see how crash recovery, you can still kind of use the same idea as before, but you have to make some modification. Okay? Okay, so that's an example of, first of all, it's an interesting algorithm. Leader election is actually useful, an eventual leader election. And it's also to show you kind of how to write code for partially synchronous system. Okay. Now, let me do one more thing today, which is a little bit more mathematical, because we're going to be looking at things that are possible and things that are impossible. And sometimes small changes will change that. And that's why it's important that we can compare problems. And this is a concept called reductions, problem reductions. This is a kind of general mathematical concept that is actually known in many areas, but we're going to apply it for distributed algorithms. We say x, so there's a kind of funny less than or equal symbol here with a curved. X is reducible to y. That means x and y here are problems, are like that we want to solve, like leader election or consensus or broadcast, okay? And x is reducible to y means that if you have a solution for y, if I have an algorithm that implements y, then I can use it to solve x, okay? X is reducible to y. So we're kind of comparing the strengths of two problems, okay? X is somehow easier than y here, or maybe exactly as hard as y, but not harder, okay? So x is like an easier problem. So this less than or equal is like ordering problems in terms of hardness, how hard they are, okay? So this is a very important concept. And we're going to use it a lot because in distributed systems, it's kind of very subtle. If you change the model, if you change one property, then maybe something gets very hard or very easy. So it's kind of very fragile like that. And so we have to compare problems sometimes, okay? So I want to kind of study this thing. What does that really mean? X is reducible to y. A little bit study the properties of that, okay? And it's to do that, I want to introduce a little bit of mathematics. I want to introduce the concept of a pre-order and also a partial order to compare. So a pre-order, so here's a little tilde, okay? This little tilde is a pre-order on a set A for any x, y, and z. X is connected to x, so that's reflexive, but also it's transitive. If x is connected to y and y is connected to z, then x is connected to z. But that's it. It's reflexive and transitive. That's all. That means x is somehow related to itself, but it also, if you can make a transitive relationship. This is a kind of simple thing, connecting two entities. But it's related to partial order. Remember a partial order? A partial order compares two things, but sometimes they're not comparable. So like causality is a partial order, for example, the vector clocks or whatever. A partial order is a pre-order with something added. If I have x is connected to y and y is connected to x, in the partial order, I know that x is going to be equal to y. Okay? If x happens before y and y happens before x, then x and y is the same event. Okay? So in a partial order, if two different objects cannot be symmetric, it's the same object. We can't have x connected to y and y connected to x for two different x and y. So in a partial order, that's not possible. But in a pre-order, it is possible. We can have two things that are connected in two directions, but it's not the same thing. Because in a pre-order, it works, the example is problems, okay? So our reduction, reducibility, is a pre-order. And it's easy to see. If I can solve x, then I can solve x by using x. That's pretty straightforward, huh? X can be solved given the solution to x. Good, so it's reflexive. Transitive, if x can be solved using y and y can be solved using z, then x can be solved using z. So that's easy. I take my implementation of z, I use it to implement y, and I use that implementation of y to implement x. So it's transitive. Reducibility is transitive, but it's not a partial order. It's not anti-symmetric. I can have two different x and y be equivalent. Remember we had our total order broadcast and our consensus? This is in the very first lecture. And we showed that one can be reduced to the other. But we also showed the other thing. That consensus can be reduced to total order broadcast. So in fact, these two, you can somehow see they're equivalent. But they're not the same problem, They're not the same. They're just equivalent. Okay? So we write x is equivalent to y. So this is like an equal with a little tilde there. If it can be reduced in both directions. So total order broadcast is equivalent to consensus. But it's not the same problem. You see that? If it was a partial order, it would actually be the same thing if they're in both directions. But for reducibility, it's not like that. Two problems can be equivalent, and they're still not the same problem. And we also can have strictly x is reducible to y, but x is reducible to y and strictly weaker. So this is exactly like a less than here. So x can be reduced to y, but it's not equivalent to y. That means you can solve x by using y, but you can't do the other way. So x is weaker, strictly weaker. So x can be reduced to y, but y cannot be reduced to x. X is strictly weaker than y. Y is strictly stronger. So you see we have some symbols here. Equivalence, but also the strictly weaker. We have three different kinds of symbols. So when we compare problems, see if we're going to be comparing problems. Okay, so let's go now to the stuff we know. Eventually P and P. Eventually P is reducible to P, right? Given P, we can implement eventually P. You see that? P is perfect. It tells me when nodes are crashing, with no mistakes. Eventually P can make mistakes. So if we have a P algorithm sitting there, we can use it to implement eventually P. We just return the results of P like as if they were a result of eventually P. And it's like the eventually P is not making any mistakes anymore. See that? It doesn't have to make mistakes, eventually P, yeah? If we have a version that's making no mistakes, that's fine. Okay? P is satisfying eventually P's properties. Eventually P will eventually make no more mistakes. P is like that, but eventually is at time 0. It's never making mistakes. So P can be used to implement eventually P. See that? So that's a comparison we can make. We can also say, in the asynchronous model, if we restrict ourselves to the asynchronous model, then eventually P is strictly weaker than P. Because we cannot implement P using eventually P. That means if we have an algorithm that makes mistakes, eventually P, we cannot somehow get rid of those mistakes. We cannot. We don't know that they're mistakes. So it's not possible to implement P when you have eventually P. In the asynchronous model. In the synchronous model, maybe, but not in the asynchronous. So this will give us some reasoning. We have to compare problems. If x is reducible to y, and if we know that x is impossible, then y has to be impossible too. Because given a solution to y, we can solve x. But if x is impossible, then y has to be impossible. Otherwise, this is not the case. Okay? So we can use it for making kind of reasoning on impossibility, okay? So if we know that eventually P is reducible to P, and if some random problem Z can be solved with eventually P, then it can also be solved with P, okay? If Z is such a nice problem that it works even if we make mistakes, then if you give it the version that makes no mistakes, of course it's going to work, okay? That's what we're saying here. But it's said in a very compact way. You see, this is a very compact way of expressing that, huh? Okay. And it's, for example, there's a question. What is the weakest failure detector that we can, that we need to solve some problem? Let's say we have some problem X. And with P, if we have P, we can solve it. Okay, fine. But P is very hard to get, huh? P is not very practical. It needs synchrony. So there's a question. Can we implement X with eventually P? That's an important question. And then we're going to, throughout the whole course, we're going to try to go from P to eventually P, yeah? In fact, we're going to show you an algorithm that works with P, and then we're going to say, but what we really want is an algorithm that works with eventually P, okay? And sometimes we can use reductions to prove that, okay? Sometimes we know enough that we can prove it using reductions, okay? For example, we might know that X reduces to P. That means we can solve X using P, okay? But can we solve X with a weaker failure detector? That's the €1 million question, okay? That would be very nice. That means X will run on the internet, okay? Whereas this one, it's not running on the internet, but if it works with eventually P, it'll run on the internet. Or maybe it doesn't. Maybe eventually P is strictly weaker than X, okay? There's a strict in there. Okay, to show that we want, let's say that P, X really needs P, okay? And so P is the weakest. X will not run on a weaker one. It needs the strength of P, okay? If we prove this, if we prove that X can be used to solve P, then actually what that means is that given an X we can solve P. That means that we really need, that means P will be the weakest, okay? If P can be solved using X, we can show that eventually P is strictly weaker than X, okay? Okay, I'm not going to say more on that now because I want you to think about it, but I will come back to that. Okay, I want to do one final thing. Remember, I showed you all these failure detectors. There was P and S, and eventually P, and eventually S, and Q and W, eventually Q, and eventually W. That's a lot, and I don't want you to memorize all those guys. But it's nice as exercise to think a little bit. Remember the properties. First of all, we have these 4 properties. Strong completeness, which is a very nice and good property, easy. Weak completeness, okay, which means there's some privileged node that sees all the crash nodes. Strong accuracy. So this is the toughie. No mistakes, ever. Okay. And then weak accuracy. Okay. Which means there's one node that is the one that we're not making mistakes for. We can make mistakes with everybody else, but this one guy, we will never make any mistake. That's still pretty strong. Okay, now let's try to make some problem reductions here. Eventually P can be reduced to P. That's reasonable, right? If I have P, which makes no mistakes, I can use it as a version of eventually P, and it works, right? That means eventually P, and I write an arrow here. See that? But we can go farther. There was S. S was like P, except only with respect to one node. But there's S and eventually S. But eventually S means it starts out being weird, and eventually it behaves like S. So if we have S, of course we can use it to implement eventually S. Huh? Any problem can be used to implement the eventually version of that problem. Huh? So we have this. See the kind of games we can play here. S can be reduced to P. Well, S is only not making mistakes with respect to one node, but P is not making mistakes with respect to everybody. So clearly, if I have P, I can just pick any old node in there, and it'll be doing S. So that means S reduces to P. Okay? And the two eventual ones the same. In the beginning, both of them will be weird, so that's fine. But eventually, they'll be doing this. Okay? So that is also a reduction that works. You see that? So these four are connected like this. P is the strongest, and eventually S is the weakest. These are the two most important ones, but these two, they sometimes come up. Sometimes we have these privileged nodes, okay? Now we have the weakly complete ones, where only one node sees the crashes, okay? Okay, these weird ones. So again, we can do the go for eventually to not eventually, okay? We can go this W1, which is weakly complete and weakly accurate. Oof. You get a headache just thinking about a thing like that, okay? But from eventually, you can always reduce it to the not eventually, yeah? And you can go on like that. Let me not go too much detail. So we have these two diamonds. Out of these four, Q is the strongest, and eventually W is the weakest. Okay. Now I want to do one more thing today, and then we're done. Here we have strongly complete ones, which means that all nodes see the crashes. And here we have weakly complete ones. Only one node sees the crash. It's the privileged node, and the others don't. In fact, they're equivalent. Weak completeness and strong completeness are equivalent. We can go both ways. That's interesting, huh? Weak completeness means only one node sees the crashes. Strong means everybody sees it. So of course it goes like this. This is trivial, huh? If we can do this, if all nodes see it, of course one will see it, huh? The trick is going in the other direction. Strong completeness can be reducible to weak. That means if I have an algorithm that is weakly complete, I can make it strongly complete. They're equivalent, actually. So these are equivalent. So all these, actually, we don't really need them, which is lucky because I don't really want to keep using them. Okay? So weak complete and strong complete are equivalent. So I'm going to, okay, so how can we prove that? I want to get some intuition, show you some intuition for you. Okay? So weak complete reduces to strong complete. That's easy, okay? Because strong complete, all nodes see the crashes. Weak complete, one node sees the crashes. But clearly, if we have this, if all of them see it, one of them sees it, okay? But the trick is the other way. How do we go from this direction? We have strongly complete, and we have an algorithm that where one node sees all the crashes. But somehow, we want all the nodes to see the crashes. How can we do that? If one node sees the crashes, how can we get all nodes to see the crashes? Now maybe you can let your imagination go. If I have an algorithm here where one node sees the crashes, how can I make all the correct nodes? How do I do it? We can actually do it. How do I do it? And it's not even that hard. Yeah?
The privileged node communicates the information.
Yeah, the privileged node just when it finds out what are the crashes, it just broadcasts that to everybody else. And then everybody knows. So simple. Okay? So that means they're actually equivalent. Every node will broadcast the suspicions. Okay? And when you receive it, when I receive it, I can get the suspicions, but I also know that node Q is alive. Huh? Every crash will eventually be detected as seen by all correct nodes. Okay? Because the weak one will broadcast to all the nodes. So weak and strong are actually equivalent. Okay? Now there's still one small detail here. We show that these two are equivalent, but because this one will be broadcasting, we have to make sure that that's not going to break any of the accuracy properties. Will that not add mistakes? That will not create extra mistakes. But that's actually kind of easy. We have to show that the accuracy are not violated. Okay? So assume that both detectors are strongly accurate, so no one is ever making a mistake, and therefore, if we send information from here to there, this information will have no mistakes, so whatever this guy receives will have no mistakes. So it will not be spreading inaccuracy. Okay? The other one is slightly different. Okay? Weak accuracy means everyone is accurate with respect to this one privileged node. Okay? And therefore, no one will make mistakes with respect to that node, because that's so we will not have inaccurate information about that node, so the weak accuracy is maintained. Okay? Okay? And then, to really make it finished, you have to talk about what about the eventual cases. The eventual cases, it's not that hard because during the first period of the eventual, there will be lots of weird stuff going on. But after that, the mistakes will be corrected. So that's it. That means this is the final diagram. This beautiful weird cube here where we have strong and weak detectors. P and Q are equivalent, they're the strongest. And eventually S and eventually W are the weakest. All that, okay, this I'm going to skip. This discussion of omega. All that, and in the rest of the course, we're basically only going to talk about two of them. So these are the only two you have to really get, P and eventually P. So this is what we're going to do in the rest of the course. These are all the different things we're going to look at. Okay? Fail stop, fail silent, fail noisy, and fail recovery. Fail stop means I have crashes, but I have a perfect failure detector. Fail silent means I have crashes, but no failure detector. Fail noisy means I have crashes, but eventually perfect failure detector. So the three things that change is the failure detector. So this is basically what happens when I crash and I'm in a synchronous model, then I have P. I'm good. What happens if I crash, but I'm in an asynchronous model? There's no failure detectors in an asynchronous model, sorry. No failure detectors. And what if I crash, I'm in a partially synchronous model? Then I have eventually perfect. So these are the three ones that are interesting. The fourth one is because of database, okay? You can also have failed recovery. Okay, and now the final takeaway for today. The rest of the course you can summarize. The whole thing can be summarized like this, from P to eventually P. We're going to make algorithms for P, and then I'm going to see how to make it work for eventually P. So it's actually easy to make the algorithms for P, okay? But what we really want is algorithms for the internet, of course. We want the eventually P. So the trick is, how do you go from P to eventually P? This is like summarizing more than half of what people do in distributed systems, okay? How do you get an algorithm that works for eventually P? That's what you really want. That's the internet algorithm. But the one you have is P, which is it's easy, but it's not internet. Okay, so the trick is from P to eventually P. And that's it. That's the final takeaway for today. So now I let you go. Thank you.